Live. All right, we are live. So I have the first questions for this week. I have 1, 2, and 3. So the first one says a system can have a non-zero velocity while the net external force on it is 0. Describe such a situation. And so I was saying that as long as the net, like if there's a pull, if the pull and the friction on the x-axis are equal and the gravity and the normal forces on the y-axis are equal, then we can have a non-zero velocity while still having a net force of 0. So as long as they're equal, an object can be moving, but there's not a force. And so like on a slant or something, like there's not really, I guess there's a force of gravity acting upon it. But I don't know, that's just what I put. I don't know what you guys think.
I agree. And then question 9, that'll be demonstrated in that question. There's a rock climber that is basically showing how that equals 0.
Okay. Then for number 2, so it talks about an astronaut in space, and I got part A pretty easily, but part B, I was talking to Mason about it a little bit before, and maybe you guys can kind of help me to understand, because I struggled with this one. But anyway, so part A says that there's a net external force of 50 newtons, and you're trying to calculate the astronaut's mass, and you're given that the acceleration of the astronaut after the force is exerted is 0.893 meters per second squared. And so I put it into the force equals mass times acceleration formula, and I got that it was 56 kilograms. And I can share my screen too. That way we can see what I'm looking at.
Is it just the Google Doc you're looking at, or?
Yeah, this is a Google Doc. So I mean, I guess you guys could look at it if you want to, rather than look at mine. But anyway, so to solve for the mass, I took the net force and then divided it by the acceleration, and I got 56.0 kilograms for the mass. Is that one all right with you guys?
Sounds good to me.
Okay. Yeah. So then for part B, it says, by exerting a force on the astronaut, the vehicle in which they orbit experiences an equal and opposite force. Discuss how this would affect the measurement of the astronaut's acceleration and propose a method in which recoil of the vehicle is avoided. And so I was thinking about like how it is going to have the same force, but because maybe the mass of the vehicle is different, it's going to have a different acceleration. Like we talked about with the truck and the car, when they are, if they're to impact each other, they're going to have the same force. But I just don't know a method in which we could recoil, in which recoil of the vehicle could be avoided. So like, I don't know, do you guys have any ideas about that?
Well, practically speaking, like in real life, couldn't you just like turn on the jets or something?
Turn on the jets?
Yeah, like increase your own acceleration. So if you're in the vehicle and you need to reduce the effect from the opposite force that's going to try to make you go backwards, then what you do is just like turn on the engine and turn on your little jet thingies, I don't know the proper term, so that you accelerate at a higher rate.
Yeah. So I guess what I'm understanding the question to be is like, how do they single out the, well, I mean, I don't know. See, I'm having trouble because the first part that says, how does it affect the measurement of the astronaut's acceleration? Like, I would think that to mean, like, how do we, like, discount the vehicle in which the astronaut's in to just get the astronaut's mass? But I don't know. Like, I guess, I don't know. You might be right about that. Maybe I'm just not understanding the question fully.
I think the question, at least when I first read it, it sounded more just like critical thinking and less like math.
Okay.
And so, like, I don't think they're looking for an exact math problem or for us to figure out numbers. I think this is just what I think. I think it's just like, you know, speaking in layman's terms, just very normal, non-mathematical things.
Yeah.
Yeah, looking at it now, it's like by exerting a force on the astronaut. So okay, that you're putting a force on the astronaut. The vehicle in which they orbit experiences, and so it's basically saying the vehicle that they're in has no, you know, forces equal or opposite. So you're putting a force on this astronaut inside this ship. So how would you counteract, you know, that moving astronaut without it, like hitting the wall of the vehicle, or, you know, that recoil, something bouncing it back?
Yeah.
Like you add a force onto the rocket, so now the rocket and the astronaut are both moving together.
Okay. Yeah, I like that. I think that's a good combination of what everybody's saying. I'm just gonna figure out how to write that. I can do that in a bit and type it in afterwards. But so, well, I guess I should do it now. So if we add a force to the rocket, then all right, I'll just add it. So if we add a force to the rocket, it can kind of move with the astronaut.
I think it has to be equal to the force of the astronaut too.
Okay. A force to the rocket, that is, oh yeah, equal to the force applied to the astronaut.
Yeah.
Then we can avoid recoil. All right. And then, so for number 3, so it wants to figure out the magnitude of the force that the motorcycle exerts backwards on the ground. And so I just wrote here what we know, that acceleration is 3.5 meters per second squared at 90 meters per second velocity. Oh, it's kilometers per hour, but anyway, it doesn't really matter. And then, so we know his mass, so we can determine his force needed to go that when he's going that acceleration at that weight. And then if we add that to the resistance, then we should get the total amount of force needed, the magnitude of the force that the motorcycle exerts backward on the ground. And so I just kind of did an equation here that says, like, the total is equal to the resistance plus his force. And so then I solved for the force that he exerts, and then the resistance, and I added them together, and I got 1,260 newtons. I don't know what you guys think about that.
Looks right to me.
Okay. Cool. Well, and that's what I have. Those are my 3 to explain. Do you guys have any other questions about any of those?
Makes sense to me.
Okay. All right. Who has 4?
I have 4 and 5. So on number 4, an American football lineman reasons that it is senseless to try to outpush the opposing player, since no matter how hard he pushes, he will experience an equal and opposite force from the other player. It says that when you choose Newton's laws and draw a free body diagram of an appropriate system to explain how he can still outpush the opposition if he is strong enough. So this was actually, let me know if I need to do anything more, but it seemed pretty simple because force overall is mass times acceleration. And so when we're thinking about getting strong enough, we're adding mass to the football lineman who's trying to outpush the opposing player. And so when they're pushing against each other, the one with the larger mass will accelerate not as fast. And so when they're trying to move, when they're moving backwards, they won't go as fast. But if they have more mass and they're pushing the smaller player is going to have more acceleration in that backward direction because there's less mass. And so you can get them further, if that makes any sense. So the forces are still equal, but one player has more mass and less acceleration in the backwards direction, and the other player has less mass but more acceleration. And so if you scroll down, you'll see my free body diagram, and I have two x directions. One of them demonstrates the two equal forces, the force of one player pushing and the other force of the smaller player being pushed. And then you have the acceleration of the larger player that is pushing, also getting pushed by the small player, and they're moving backwards, but their acceleration is smaller because they have more mass. And the acceleration on the other side is larger because they have less mass. So, does that make sense?
Yeah.
Pretty simple.
Yeah.
Number 5, this one was a lot harder for me to figure out. So, especially on number A, please, if any of you think that this sounds weird, let me know, because I actually just had to Google it. So a rugby player is inadequate and is being pushed backward by an opposing player who's exerting a force, and this is the net force of, well, not the net force. Anyways, it's the applied force of 800 newtons. And then the losing player plus equipment is 90 kilograms, and he's accelerating backwards at 1.20 meters per second squared. The first question is, what is the force of friction between the losing player's feet and the grass? And so this is the one that I had to look up, and I found that when you're on the x-axis, or when you have a diagram, then obviously the forces have to equal out. And so you have your net force. Net force equals applied force minus frictional force. And so the net force is going to be found, it's also, you could call it like the normal force or whatever, but the losing player plus his equipment, which is 90 kilograms, multiplied by his acceleration is 108 newtons. And so that is the overall net force, you know. And so the applied force is 800 newtons, and then when you do all the math and change everything around, then it's 800 newtons minus that 108 newtons, which is the net force, equals the amount of frictional force that's working against the applied force. And that came out to 692 newtons as a frictional force. But once again, I'm not sure on that. So do any of you have any other ideas on that, or?
That's what I got too.
Oh, really?
Yeah.
Okay. Yeah, because I'm super unsure about that one.
No, yeah, that's right.
Okay, good. And then we have our little diagrams down there. But question B, what force does the winning player exert on the ground to move forward if his mass plus equipment is 110 kilograms? So the force that he's applying to the ground is just what we call weight, and that would be his mass times the acceleration of gravity, and then that equaled out to well, that would be newtons, 1,078 newtons of force that he's applying on the ground to move forward. Does that seem right? I'm reading back, but
I think so.
newtons. Hey, thanks for deleting that for me.
No, I'm sorry. I don't know if you were working on it or not.
I was just about to do that. So yeah, that's the force at least that he's applying to the ground.
Okay. That sounds right to me.
Same here.
All right, who's got 6?
I had 6 and 7. Okay, yeah. So I just pop my answers in there, and then I have my work on the pictures I attached. All right, so suppose a 60-kilogram gymnast climbs a rope. A, what is the tension in the rope if he climbs at a constant speed? And so this was just your mass acceleration equals tension minus mass times gravity. So I have that equation, then I rearranged it so I had it, oh no, never mind, because ma is 0, because acceleration is constant, so I just set it to 0. Because you could assume he's not moving, or he's moving at a certain speed. It's easiest to just say he's not moving at all, since it's a constant. So 0 equals tension minus mass times gravity. So then I just plugged in the equations that they gave us in the problem, and the answer came out to 588 newtons. And then for B, what is the tension in the rope if he accelerates upward at a rate of 1.5 meters per second squared? So it's the exact same formula, except now we have an acceleration that's not 0. So you just plug in the same equation, you just plug 1.5 in for meters per second squared. And then plug in all your fit numbers and solve for tension to get 678 newtons. So 6 was pretty straightforward. Did you guys get the same thing, or is anything?
Yeah, must be good.
Okay.
That's good.
So
I
7.
have a question really quick. Looking at your equation, so you said mass times acceleration equals tension minus mass times gravity?
Yeah.
So then when you put them both on the same side, when you like just took tension out and solved for tension, shouldn't it be added? Shouldn't mass times acceleration be like plus mass times gravity? Or am I looking at it wrong?
Let me see. Mass times gravity.
Oh, I see what you're talking about. Yeah.
Okay, so if you see the equation at the very top left, ma equals t minus mg.
Uh-huh.
I drew an arrow to the right where I just replaced mg or ma with 0.
I see.
So then I just added mg to the other side, so it's t equals mg. Because m times 0 is 0.
Right. I'm talking about part B.
I'm sorry.
For part B? Oh.
Okay, let's see.
Because see, the top.
Oh, you're so right. Oh, good catch.
Okay.
Oh, where's my calculator? Good eye. Holy cow.
That's why we're doing it together, right?
Yeah, see, I was doing too much of the same thing in B. Okay, so that would be...
So you should be adding it then, right?
Yeah. 60 times 9.8.
Actually, I still got the same answer. Wait,
Really?
maybe not. Hang on. Maybe I'm just doing it wrong.
Yeah, I got the same answer too.
Yeah, so maybe you just forgot to
I
write
must have done it right, but wrote it wrong.
Yeah.
I have a bad habit of doing everything on scratch paper and then trying to make it look nice on these things.
Oh.
That's probably what happened. I'll just attach a new picture with the fixed equation.
Yeah, sounds good.
Okay, anyways, moving on. So 7, I had a bit of a hard time with. Well, as far as B goes, A wasn't too bad. But B, I have a hard time sometimes understanding what to do with friction. So we'll get there. So A, commercial airplanes are sometimes pushed out of the passenger loading area by a tractor. An 1,800 kilogram tractor exerts a force of 1.75 times 10 to the 4th Newton backward on the pavement, and the system experiences forces resisting motion that total 2,400 Newton. The acceleration is 0.15 meters per second squared. What is the mass of the airplane? So correct me if I'm wrong. So I have a little picture. And so then for the total force, the F net, I took the 1.75 times 10 to the 4 that's exerted by the tractor. And then resisting that force, let's see, and the system experiences forces resisting of 2,400. So I just subtracted that out to get a total F net of 1,500 or 15,100. So then I use the equation m equals F net over acceleration. So mass, to solve for mass. So then that's 15,100 newtons divided by 0.15 meters per second squared, which comes out to 107,000 kilograms. Now, correct me if I'm wrong here, but that's not for either, that's just for the whole system, right? So that's just 107,000 kilograms in the system, and we know that the tractor is 1,800. So then we have to subtract out the tractor's weight to get the total airplane weight.
Mm-hmm.
Yeah.
Okay, so then A, I got 105,000 kilograms for the airplane. Okay, so B, this is where I was a little confused. So I used the F net equals MA equation. So I plugged in the mass of the tractor and then the acceleration that it has to solve for the net force. And it came out to 270 newtons. But then the problem, B also says, okay, so calculate the force exerted by the tractor on the airplane, assuming 2,200 newtons of the friction is experienced by the airplane. So there's 2,200 newtons of friction as the tractor's trying to pull the airplane. So then doesn't the tractor also have to overcome that force? So I didn't know what to do with that number, to be honest. Anybody know?
I could be wrong, but I do think you do have to include it. Wouldn't you just add it in?
Well, so that's what I did to get 2,900 newtons, because it can't be the force it's exerting minus the friction, because then you'd have a negative newton, which can't.
It would have to be, yeah, the other way around. Because if if the tractor's going to move it, it has to overcome friction while still, moving it, and so it's going to have that force, its own force plus the friction.
Okay.
Going in the opposite direction. So I would think you'd add them. I don't know. Does anyone have a different idea? Yeah. So that's what I think.
Okay. And then C was just to draw free body diagrams for the truck and the airplane. So I have the truck at the left and the plane on the right. And so, of course, they have like the normal force pushing up and then their weight pushing down. And for the truck, it has its acceleration moving it forward and the force of the plane holding it back. I don't know if that was supposed to be friction. I'm not positive what needs to go there. So I put the force of the plane, like the weight of the plane. And then for the plane, it has the friction that it's running against, and it has the force of the truck pushing forward.
Yeah, that looks fine to me. What everyone else thinks?
And that was it for mine.
Okay.
Okay. Number 8. All right, so this one talks about a car being stuck in the mud, and it's tied a rope to a tree, and it wants to know kind of the newtons of the force being pulled out. For the part A, it was asking what is the, for the center of the rope of the car at a 2-degree angle. And so basically I just took the newtons that it gave me, which was 12,000, and I times it by the sine of 2, because the angle was 2 degrees. And that gave me 418.79 newtons, but that's only half it, because that only gives me the first part of the kind of diagram there. And so I had to times it by 2 to get the full force. And so therefore, I didn't add in there. Give me the full force was 837.58 newtons for that rope. And then for part B, I wanted to know what force would be exerted on the car angle at 7 degrees. So basically it was the same thing, but just now with a greater angle. And so I took that 837 and divided it by the sine of 7 for the angle change, and then it came out with 6,872.77 newtons for that angle. Does that make sense?
Looks good.
Yeah, that makes sense.
Yeah. Stop me if you have any questions, I guess.
Yeah, that looks good.
All right, this next one was fun. This took me a little while to figure out. I don't know why. Once I figured it out, it's real easy. But so there's this rock climber. She's standing still on this rock face here, and they want to know what the tension of the rope is, and then kind of the friction between her feet and the rock wall. And so I don't know if you guys see the Google Doc, but on there I drew another little diagram next to it to kind of give me some ideas of what kind of formulas I would use. And so I kind of drew the diagram to figure out the forces of that, and then underneath I put the equations I use. The top two were F equals and T equals. Those are the answers. I tried highlighting them, but I couldn't get it to highlight. So if anyone can do that, that'd be awesome. So anyway, so what I did is I had to find f of x and f of y. And so what I did is I basically found one first. So I found the tension first, and then I took that tension and put it in. Or no, I found friction first, and then I put it in to the equation, and then solved for the tension. And after I did that, I came out with the answers of friction 693.7 newtons, and then the tension was 1,154.34 newtons.
So you're trying to highlight what?
I was trying to highlight the top ones where it says F equals, and then it says
Yeah.
and T equals. I was trying to highlight that because that's the answer.
Yeah, I just bolded my answers.
Oh, did you? Man, just do that then. There, I bolded it.
You can change it to red too.
Oh,
Yeah.
there we go. That works too.
That's true. Maybe I'll do that for mine too.
But yes, that's what I did.
I'm just looking through your work, but it sounds right, like the right way to work. Looks good.
Okay, number 10.
All right.
So when a glass bottle full of vinegar warms up, both the vinegar and the glass expand. But the vinegar expands significantly more with temperature than glass. The bottle will break if it is filled to its tightly capped lid. Explain why, and also explain how a pocket of air above the vinegar would prevent the break. So basically with this one, glass has a 70 times 10 to the 9. Funny to put in. It's newtons over meters per second on the Young modulus tension and compression scale. So that's basically all like hold any kind of glass. So basically, thank you.
You said meters per second?
Yeah. Or sorry, like meters squared. I don't know why I said meters per second.
Oh, you're fine.
But eventually, the reason the tension in the glass with the vinegar, because in a liquid, all the molecules have to stay together. They're forced together. But when they're forming into a gas, like when it's being heated up, they need to spread, and that's what the heat is doing. So basically, the glass is trying to suppress that gas form, but eventually the tension overcomes the heat, but it causes more tension in the vinegar. Eventually the tension overcomes the suppression, it will break the glass. Basically there's this force that's creating the tension from the heat, and that is affecting the vinegar and the glass. When the glass is heated, it will expand, which will cause the glass to deform or break in the tension, to relieve tension buildup. Basically, having the pocket of air would allow for the molecules to spread more during the heating period without breaking the glass, because it's giving more room for that expansion and less tension. So I'm bad at explaining things, but
Yeah, no, that makes sense. It's kind of an interesting question because it's very conceptual, but very different than what we've been doing. So good job with that one.
thanks.
Any questions on 10?
That looks good.
So 11 was fun to figure out. So basically, I don't remember what the formula is called, but you see like the triangle and the L. That is the amount of deformation that occurs when the antenna is being compressed with the still cylinder, not small radius. So, and the LO is the original length of the still bar in the antenna. Trying to like go down this, and then Y is basically it's a factor that can play into any kind of these equations. In this case, the factor is the steel. That's what's creating the tension and the compression. Yeah, and then A is the cross-sectional area. So basically, still on the Young modulus tension compression scale is 210 times 9 to the 11th newtons per meter squared. Or I just want to not have to work with such a 210, so I put 2.10 times 10 to the 11th, which is the same exact thing. And then, so in the original length of the antenna is 610 meters, so that's going to be that original length. And then the F, which is basically the mass and the gravity, you're going to take the 72 plus 400 times it by gravity, That's going to give you 4,625.5. And then you need to find y, which is the still cable, which is the 2.10 times 10 to the 11th. And then to find the area, you're going to do pi times radius squared. So in this case, it's the 0.150 meters squared, which gives you 0.07069. Part is probably the most confusing part. So the formula is the original line times f over y times a, which is 610 meters times 4,625.5 divided by 2.10 times 10 to the 11th times 0.07069. And that's going to give you 2,821 over 555 over 1.4844 times 10 to the 10th. And that's going to give you 0.000190 times, but with the leftover, you need to do 10 times 10 to the 4th, which is going to give you 0.190 as the tension and compression, or how much is being compressed at that time.
Wow. That was impressive.
Wow.
That was impressive.
I trust you.
Yeah, as I walk through it with you, it looks awesome.
Is it raised 10 to the 4th or is it -4?
Oh yeah, sorry. Yeah, it would be -4 because you're trying to. Well, hold on.
Well, actually,
No, I think you're right. You're right.
yeah, because if
Okay,
you
I was just
put
thinking
it on
about
the other one, if you put it on the
okay.
0.19, yeah, it would be negative.
That's good.
Yeah.
That looks good to me. Awesome.
Cool. All right. Anyone have any questions about any of those?
I'm good.
I'm
I
good.
thought
Good.
that was pretty impressive.
Sweet.
Okay.
So I guess next week we have 9 questions. I don't know how you guys want to do that.
The other thing that I was telling Mason earlier too is that I saw that Brother Johnson mentioned on an announcement that it's better if we have more than one person working on each problem so that the two, when they share, can compare their answers, see how well they did. And so this is a good one because there's only 10 problems. That maybe, how would we do that? If we each took...
Yeah, that still makes it really hard. I don't know. Maybe it's just we all of us individually do all the questions, but only a certain amount of us post what we got.
We could do that. Yeah, because that's pretty much what I did this week.
Yeah.
I did the majority of them, and I looked at all of them. So we could just do that.
Does that sound good with everyone?
Yeah, it sounds good.
Yeah.
Okay. So who wants which questions this week?
I can take 1 and 2.
Okay.
I can take 3 and 4.
I'll do 5 and 6.
Okay, and then we have 3 left, so 7, 8, and 9. Who wants to just do one? I can just do one, or who was the other one that doesn't have any? Landon?
Yeah, I'm trying to pull them up, and it's really bad right now.
Yeah.
You can take the 1. I can take the 2.
Okay, because it depends on if there's like conceptual questions too.
Mm-hmm.
8 is 3 parts. Oh, what if I did 7 and 9 and you did 8, Landon?
Let's see.
Because 8's pretty long.
Sounds good.
Okay. So then I'll do 7 and 9.
Okay, so we'll each do and post our own, and then do them all for comparison.
Sounds good.
Yep.
All right, I'm gonna end
Sounds
the
good.
broadcast. All right, thanks, guys.